Please, if you're in the class, please do well to drop a message in the comment section. If you are on the call, please do well to drop a comment in the comment section. If you're in the call, please do well to drop a comment in the section. Do well to drop a comment in the comment section even as we kick off. If you're in the call, please. Okay, I can see one already. Let's keep it coming. Let's keep it coming. If you're in the call, let's drop a comment. I'm in the call already. Let's drop a comment. All right. Okay. Okay, so we'll quickly start. We have just 2 hours. We have just 2 hours more. Okay, so we'll keep start now. Please, like I indicated in the description, let's get our notebooks. Let's get our calculators ready. Let's get everything we actually need, especially questions relating to its measurements and its capacity. If you have questions before now that is giving you tough time on its measurement and its capacity, please do well to drop them. Please do well to drop them. If you have any questions on its measurements and its capacity, do well to drop them in the comment section. Do well to drop them in the comment section. We'll go through them as the class goes on. All right. We'll be kickstarting now. If you know someone that is not yet on the call, please give them a call. Let them join us. They're already missing out. Give them a call. Let them join us. Let them join us. We are about starting. When we start, we're not going to look back. Straight forward, straight course. All right. So if you know someone that is yet to join, they should be here by now. Someone who is here to join the call, tell them that they're already missing out. Okay, please let me check from your hand. If you can drop a comment from your hand, let me check, please. If you can drop a comment, let me know, please. Is the comment section open? Let me to check. Can you comment from your hand? Okay. All right. Okay, I've gotten an update. You can't comment just yet. All right, so this is how we're going to do. If you have a question, just send it to send it to my WhatsApp number 081. If you do not have it, send to my WhatsApp number 081 21 21 6596. 081 21 21 6596. If you are not in Nigeria, you can use the call code plus 234 plus 234 21 6596. If you're not in Nigeria, drop your questions on my WhatsApp handle. All right, so let us proceed. I'll be coming to this board now, so let's proceed. All right, good evening to you all that has made it a time to learn physics. I must say you are welcome. Welcome to today's class. Today's class is going to be awesome. Today's class is going to be amazing. I just need you to be very attentive throughout the class. Remember, like I will always say, there are only smart students, and one thing that smart students they do is that they pay maximum attention whenever a class is going on. That is what differentiates those guys that top the class and those ones that seem not to. All right, that is the ability to listen and to participate through a class. So I want to urge us, please, let's stay participating. If your phones will be a distraction, please, if your WhatsApp or other social media platforms that you have on your phone will be a distraction, you can please do well to take them away. All right. So once again, you're welcome to Physics Clinic with the Polyamine. All right. And this Sunday afternoon, we're going to be treating the topic heat measurement and heat capacity. Some of us, to us, this concept is not a new concept. It's something that we know before now, but maybe there are some great areas that we are still struggling with, that we are still struggling to understand. Some great areas that we are still struggling to understand. This afternoon stroke evening, I will help you erase those gray areas. I'll help you make it become clearer. I'll expose you to much more clarity on the concept heat measurement and heat capacity. All right, so let us begin. When you hear the word heat, what comes to mind? When you hear the word heat, what comes to mind? Or better still, when you hear the word heat transfer or heat flow, what comes to mind? All right, so basically, when the word heat is mentioned, what actually comes to my mind is a form of energy. That heat is a what? Is a form of energy. And how does this heat flow? This heat flows by moving from a body at a higher temperature to a body at a lower temperature. Okay, so we say that heat is a form of energy that flows from a hotter body to a less temperature body. All right, so from that singular expression, from that singular explanation, we see that it is almost impossible to talk about heat without mentioning temperature, and it's also impossible to talk about temperature without considering heat, because when heat is applied to a body, it causes, there is no particular effect of heat which is a raise or a change in that body's temperature. So when heat is applied to a body's temperature is observed to increase, and when heat is removed from a body, that body's temperature tends to drop. All right, so there's no way you can talk about it. We're talking about what? We're talking about temperature. All right, so it is a form of energy that flows from a hotter to a colder body, or a body at a lower temperature. Okay, so the amount of heat that a body can possess at a particular time, the internal energy that a body can possess at a particular time depends on three major factors. Depends on three major factors, and that is one of them is the mass of the body. The mass of body, that's M. The mass of that particular body. Then another one is the nature of the body. The nature of the body. Let me put it that way: how receptive this body is to raising its temperature. How receptive the body is in raising its temperature is known as the nature of the body. And this nature is considered when we consider the specific heat capacity of the body. All right, how receptive a body is to raising its temperature quantifies or falls under the nature of the body, which has to do with the specific heat capacity of that body. The specific heat capacity of the body. We'll come to this later to talk about what this really means. All right. Then the third one is the change in temperature, delta theta, which is final temperature minus initial temperature, because whenever heat is applied to a body, it causes a raise in the body's temperature. So if the body is at a lower temperature, when heat is applied, the body's temperature increases to a higher final temperature. But it's a situation where we are removing heat from a body. In a situation where we are removing heat from a body, such a situation results in the final temperature being less than the initial temperature, what we call a loss of heat. Loss of heat brings about reduction in temperature, while a gain in heat brings about increase in temperature. All right. So if the heat energy a body can possess or a body can supply depends on these three things I mentioned earlier: the mass of the body, the nature of the body, which is a measure of its specific heat capacity, and the change in temperature that will be observed in the body. It therefore means that heat supplied or heat quantity is given as the mass of the body, represented with the letter M, and the specific heat capacity represented with the letter C, and the change in temperature, delta theta, which is theta 2 minus theta 1. Do not forget what each of these quantities means here. I mentioned earlier that the M stands for mass, the mass of the body. The C stands for the specific heat capacity, and here our delta 2, like delta 2 rather, is our final temperature. Our final temperature. Theta 1 gives us the initial temperature of the body. Okay, so whichever one happens, if a body's initial temperature seems to be greater than its final temperature, it means that that body has lost an amount of heat in its temperature. When the body's initial temperature is greater than its final temperature, theta 1 is greater than theta 2, we say that this iteration is called heat loss. Heat loss. It is lost in that situation. But when theta 2 is greater than theta 1, this results in heat gain. This results in what? In heat gain. Alright. So whichever process is taking place, a loss in heat represents a situation where initial temperature is greater than the final temperature, while a gain in heat takes place in a process where the final temperature is greater than the initial temperature. All right. So earlier on, I mentioned, let's continue. Earlier on, I mentioned that heat is a form of energy, and like we all know, all forms of energy cannot be destroyed. Actually, cannot be destroyed. One thing that can happen is that if the energy can be converted, can be transformed from one form to another, but can never be destroyed. All right. So if a body is losing heat, that heat is being lost, is not actually lost. Sorry for this spelling. It's not actually lost. All right, it is given off, and another body receives it. Just like we are heating water, we are using an electrical heater or an immersion heater. When we place the immersion heater has its source from electric source. Understand? So it gives us, it converts rather electrical energy. In that state, it converts electrical energy to heat energy. All right. So the electrical energy from the immersion heater is converted to heat energy, which causes the water to become warm until it gets hot, even down to its boiling point. All right. So the heat loss is always equal to heat heat gained at every time. Heat lost is always equal to heat gain. Let me give you an example quickly. Now, you come from, should I say, outside is actually pretty hot because sun is shining. So the outside environment from your house is actually very hot. So the moment you step into your house, and your house is pretty much air conditioned, the moment you step into your house, now what happens is your body is at that point, because you're coming from a hot environment, your body is at an higher temperature. The moment you step into that air conditioned room, how does it flow again? It flows from a body at a higher temperature to a body at a less hot body, or a colder body. Right? So at that point, you tend to lose heat to your environment. You are the one losing heat at that point, while your environment is gaining heat. Alright? So your body is at a higher temperature than the room that you walked into. So your body will tend to lose heat to that environment. While that environment that was at a lower temperature before then will tend to what? Increase. Add more heat. Gain the heat that your body is losing to cause a raise in its temperature. So every time there is heat lost, there is always what? Heat gained. Every time there is heat lost, there is always heat gained. Alright? So if this is true, how then can I now quantify the amount of heat energy that a body loses, or the amount of heat energy that a body gains per time? How can I measure the amount of heat a body loses and the amount of heat a body gains? Okay, now note, the body is to lose heat is actually measured in joules. Just in case, I should not forget to mention that heat is measured in joules. So if a body loses 5,000 joules of energy, to an environment, all right? Now, if all this amount of heat energy is lost, the environment will actually gain same 5,000 joules. That's the idea. So whatever is lost is gained. Whatever is lost by a body is gained by an external environment. That external environment can be anything that is at a lower temperature. It's like placing a warm bottle of water in a refrigerator. Okay, after some time, because the interior of the refrigerator is at a colder temperature compared to that bottled water tends to lose its heat. If that bottled water was containing 5 joules of energy, okay, if it loses all that heat, the environment will gain that same 5 joules of heat energy. Okay, so whatever is lost is gained. And if the amount of heat lost or gained by body is given as mc delta theta, let me say, let me call the heat lost here. Let me represent it with state 1. Then I'll represent heat gain as what? As state 2. So that will mean that the mass of the body that is losing its m1 times the specific heat capacity of the body that is losing it times the temperature difference that body will undergo. Now, for a body losing heat, I said earlier that if a body is losing heat, the initial temperature is greater than what? Than the final temperature. So instead of putting theta 2 first, I'm going to say theta 1 minus theta 2. Now this is to remove the effect of negative sign in our calculation or in our measurements. All right, if you do the other way around, you would not be wrong. All right, it will only show that your minus will only show that it was lost, just like we have it in some chemical reactions. Okay, where we have endothermic reactions and exothermic reaction. All right, so the minus will show that it was lost to the environment. Okay, but we do not want that effect. So for a body losing heat, we always place the initial temperature before placing the final temperature. Okay, so this would be M1C1 to, no, let me call this one, let me change this from M1, let me just say S. Let's assume that it is a solid body losing heat. All right, so I'll call it S. Okay, then this will be equal to, now for the body gaining heat, let me consider let me say water. Water is the one gaining heat. If I consider water as the body gaining heat, then it will be the mass of water, same formula, the mass of water times the specific heat capacity of water. And this will go into, now, will I put theta 1 first? Okay, now listen, we said that for a body gaining heat, the final temperature is greater than the initial temperature. Okay, so I'm going to leave this way. Theta 2 will be minus theta 1. All right, so this will be the representation, considering that heat is not lost, or the heat lost by body is gained by another body. All right, okay, if all of this is true, all that we have been saying is true, if all these things that we have been saying is true, then how then do I now quantify the specific heat capacity or the heat capacity of a body, which is the ability of the body to raise its temperature? Okay, what then is heat capacity? What then is the heat capacity of a body? What then is heat capacity of a body? All right. So let me quickly pen this idea to you. All right. So if I should take a cup of water, and place it on the same flame as this, and place it on an amount of heat, okay, and supply an amount of heat to it, compared to a spoon that is also exposed to the same amount of heat. Let's say I expose the cup of water and the spoon to 100 joules of heat, both of them to 100 joules of heat. Now the observation from experiment, from practice, you observe that the spoon becomes hotter, like it gets hot quickly compared to the water. It gets hot quickly compared to the water, even though they are exposed to the same heat, 100 joules, 100 joules. Even though they are exposed to the same heat, all right, it turns out that the spoon gets hotter. The spoon's temperature is raised because while a spoon is made up of a very good conductor, like of heat, like steel. All right, so the temperature of the spoon will tend to be increased faster than the temperature of water. It therefore means that the spoon is more receptive to cause an increase in its temperature. So we define its capacity as the amount of heat energy. Its capacity is the amount of heat energy that is required to raise a substance, to raise the temperature of a substance, by 1 Kelvin or 1 degrees Celsius. To raise the temperature of a substance by 1 Kelvin or 1 degrees Celsius. That is what heat capacity is all about. All right. So it takes a smaller amount of heat. It takes a smaller amount of heat to raise the temperature of steel or steel spoon compared to water. For water, will require more amount of heat. All right. So if I use this simple illustration to say that the heat capacity of let me just assume an arbitrary value for steel. If I say the heat capacity of steel is 200 joules per kilogram per Kelvin. Per kilogram per Kelvin. All right. This will mean that it will require 200 joules of energy. Understand? It will require 200 joules of energy to raise. Okay, sorry. It will require 200 joules of energy to raise 1 kilogram. Sorry, to raise the entire mass of the substance. It will require 200 joules of energy to raise what? The entire mass of the substance by 1 Kelvin or 1 degree Celsius. How is that possible? If my heat if the heat quantity in a body is given as mc delta T, heat capacity, I usually represent this as C subscript P. Heat capacity Cp is given as mc, where this C here, like we saw earlier, is the specific heat capacity, while m is the total mass of the body. So my Cp here gives me the heat capacity of the body, m for mass of the body, and C the specific heat capacity. All right. So my SI unit, mass, that's a kilogram, then here is my joules per kilogram. So if I have mass, it will be kilogram times specific heat capacity. Sorry, I did not indicate that earlier. Specific heat capacity from the first formula I mentioned, H equals mc delta theta. When I make C the subject of the formula, will give me that C is equals H over m delta theta. So from here, the SI units for specific heat capacity will be joules over kilogram per Kelvin. All right. So this is the SI unit for specific heat capacity, joules per kilogram per Kelvin. Joules per kilogram per Kelvin. All right. So if that is true, anywhere I see C, let me put the SI unit for C. That will be joules over kilogram times Kelvin. All right. So kilogram here, we cancel this kilogram. So my heat capacity Cp is actually measured in joules per Kelvin, which is the amount of heat required to raise the entire mass of a substance by 1 Kelvin or 1 degree Celsius. So if I mention steel spoon, it means that it will require 200 joules of heat to raise the entire mass of that substance by 1 Kelvin or 1 degrees Celsius. That is the explanation for what heat capacity. And every material has their own value. The heat capacity of steel is different from the heat capacity of any other material, even down to gold, aluminium. All metals have different heat capacity. All right. So please, if you have questions, you can also drop it. Keep on dropping it in my WhatsApp. All right. In the next 2 minutes, I will come and check. Okay. So please take time to digest this. Now let's see. The next thing we're going to talk about is what I had explained earlier: the specific heat capacity. The specific heat capacity. The specific heat capacity. All right. So we have talked about heat capacity. All right. So now, from the word specific, all right, it means that if a substance has a mass of 5 kilograms. Now, mind you, when a body's temperature is increased, it does not just increase the temperature at once. It takes place on the microscopic level, 1 kilogram after the other. All right. So if I am specific about the amount of heat that we raise just 1 kilogram out of the total mass, just 1 kilogram out of the total mass, that means that particular heat that can raise just 1 kilogram out of the entire mass of the body by 1 Kelvin or 1 degree Celsius, that particular heat energy is called specific heat capacity. I am concerned about just 1 kilogram mass of the entire mass. All right. So if it is 5 kilogram mass, I am concerned about just 1 kilogram out of the 5 kilograms. All right. So that's the idea of specific heat capacity. And I've given the formula here earlier. Here's the formula. C, which is a symbol for representing specific heat capacity, is equal to the heat energy required to raise 1 kilogram mass by degree Celsius or the Kelvin. All right. So these are specific heat capacity. Okay. Every material also has their own specific heat capacity. You don't get it twisted. Every material has their own what specific heat capacity. All right. So I'm going to take a break for 2 minutes. I'll come answer your questions. Please, if anything here is not clear, just drop it right now. Drop it in my WhatsApp line, my WhatsApp account. I will come read your questions and come back again and give answers. Please, so I'll go now. Do I have any questions? Please drop it on my WhatsApp. Do I have any questions? Please drop it on my WhatsApp. Any questions? Please drop it on my WhatsApp. Any questions? Drop it on my WhatsApp. I'm waiting to read them. Any questions? Please drop it on my So I'll be proceeding now. Please, let's stay connected. Let's stay connected. Also, calculators, please, you should be with your calculators. All right. Please, let's stay connected. Let's stay connected. Also, calculators, please, let's stay connected. All right. So we'll resume. We'll resume right about now. Okay. So we have seen the concept of heat measurements. All right. That to measure heat, you have to consider the amount of heat that was lost, or the amount of heat that flows from a hotter body to a body at a temperature. You must consider that. All right. That's how we quantify heat. Okay, that's how we quantify heat. And we also mentioned that there is no separation. Actually, you cannot talk about heat without talking about the temperature effect. Okay, the effect of change in temperature to produce in a body. There is always an effect. All right. Talking about temperature, you must mention heat. Talking about heat, you must mention temperature. They go together. All right. So if that is true, we now saw that the amount of heat that a body can possess, the quantity of heat a body can possess, depends on 3 major things: the mass of the body, the nature of the body, which is a measure of its specific heat capacity, that is, how much heat energy that is required to raise 1 kilogram mass of that body by 1 Kelvin or 1 degree Celsius. That's the specific heat capacity. We also talked about the change in temperature. If it is supplied to a body, an amount of there is an observable change. There's an observable change of what? Of temperature. And it's given as my equation here, mc delta theta, where delta stands for theta 2 minus theta 1. Theta 2 is the final temperature, theta 1 is the initial temperature. All right. So we also mentioned that for when a body is losing heat, the initial temperature is usually greater than the final temperature. And for a gain in heat energy, the final temperature is greater than the initial temperature. Okay, so we saw a situation where heat is lost and where heat is gained, that we need to represent for a body losing heat, we must place our initial temperature first. Theta 1 first. For a body losing heat, we must place our initial temperature first before the final temperature. Why? To remove the effect of a negative sign in our final answer. Okay, to remove the effect of a negative sign in our what? In our final answer. But when it is a gain of heat energy, when we are considering a gain in heat energy, that will not be the case, because if the body is gaining heat, its final temperature will always be greater than its initial temperature. Okay, so if that is true, it means that theta 2 comes first before what? Theta 1. Final temperature before initial temperature. Okay, so this is the concept of heat loss and what? And heat gain. Right about now, we are going to be looking at some questions. Come in and check my notes. We're going to be looking at some questions. I don't know how we're going to get particular questions, but I would really love us to take it down, please. If you can write it down, I'll be very slow so that you can get it. Okay? Please, if you are with your pen, please let me know. Let me know that you are writing. Let me know that you are writing. If you are with your pen. If you are with your pen, let me know that you are writing. Drop a message now. Drop a message now on the group that you are ready to write. Drop a message now on the group that it's your pen and you're ready to take down this question before I proceed. David, are you with your pen? Please, if you're in the charts, please drop a message that you are ready to write. All right, so I go with the first question. It says, a metal block of mass 0.5 kilograms, absorbs 4,200 joules of heat. Absorbs 4,200 joules of heat, causing its temperature to rise from 20 degrees Celsius to 40 degrees Celsius. I come again. Metal block of mass 0.5 kilograms absorbs 4,200 joules of heat, causing its temperature to rise from 20 degrees Celsius to 40 degrees Celsius. Full stop. Calculate the specific heat capacity of the melter. Calculate the specific heat capacity of the metal and the heat capacity of the block. Calculate the specific heat capacity of the metal and the heat capacity of the block. So let us see this together in the class. All right, so we'll solve this now. All right, so let's see the solution to that question. Allow me to divide my board into 3. So my solution, I'm going to see my solution. All right, so like I always say, physics is not as easy, it's not as difficult as it seems. Okay, like every other life process, when you want to provide a solution, you actually look at what you have. Okay, you must consult, what do I have? What do I have that can possibly help me What do I have that can possibly help me provide a solution for this problem? All right. So the first thing we always do in a physics question is to read the question, bring out all that is required, all that is needed. Read the question and bring out all that is needed to tackle such a question. So let's start. From the question, we see that the first thing that was mentioned is the metal block, and that metal block has a mass of 0.5 kilograms. So the mass of block is 0.5 kilograms. All right, so this is the first thing mentioned. It now says that this metal block absorbs 4,200 joules of heat. It means the amount of heat it took in was 4,200 joules. That is my heat quantity H. All right, heat quantity. That's H. Heat 4,200 joules. That's the amount of heat that the metal block took in. Now went further to say that this heat that this block took in causes a change in the temperature. Okay, it causes a raise in the temperature of the body. Remember, there is no heat. If there is heat, there must be increase in temperature, except when we are considering change of state. All right, but as far the body is not changing state, there must always be a significant change in temperature. All right, so it says causing its temperature to rise from 20 degrees Celsius, that is from theta 1, from 20 degrees Celsius. So it means initial temperature theta 1 is 20 degrees Celsius. From 20 degrees Celsius to theta 2, 40 degrees Celsius. Alright, so these are the vital parameters that was given to us. These are not the answer. This is nothing here is the answer. These are just tools, parameters we can use as a measure to obtain what is needed. So the first question A says we should obtain the specific heat capacity of the metal. What is specific heat capacity? That's the letter C. We should find C, the specific heat capacity, and B now says we should also look for the heat capacity CP. If C is not known, you cannot find CP. That's the idea. That's the idea, all right? So with all the information provided in the parameters, in all the information provided in these parameters, which of them will there be sufficient enough to obtain the specific heat capacity? The answer is yes. Why? From this formula we saw earlier, the heat that is possessed by a body, the heat quantity a body can possess, is given as mc into bracket theta 2 minus theta 1. And I am looking for specific heat capacity C. So not to waste time, specific heat capacity will be my subject formula. So C here will become H over M into theta 2 minus theta 1. Alright? C equals H, that's the heat quantity, over M into bracket theta 2 minus what? Minus theta 1. Alright, so let's get my C. The amount of heat energy that the body absorbed, 4,200 over the mass of the body, that's 0.5, times, we'll take this into a bracket. The final temperature, that's theta 2, is 40. The initial temperature, theta 1, is 20. So this would be C equals 4,200 over 0.5 times 40 minus 20, that's 20. So this would be 4,200 over 0.5 times 10. Sorry, 0.5 times 20. It's like saying half of 20, and half of 20 is 10. Alright, so this 120 joules per kilogram per Kelvin. This is the answer to question A that says determine or calculate the specific heat capacity 420 joules per kilogram per Kelvin. All right, so this for the first question, specific heat capacity. Now we proceed to the second part of the question. The second part of the question says you should find the heat capacity. All right, now we saw that heat capacity earlier on is the amount of heat required to raise the temperature of a substance. To raise the temperature of a substance, the whole substance, the entire mass of the substance by 1 Kelvin or 1 degree Celsius. And the formula we saw earlier, Cp, let me write this properly, Cp is equals the entire mass M times the specific heat capacity. And we have seen that the mass is 0.5 and the specific heat capacity that we obtained just now is 420. Okay, so not to waste time, if mass is 0.5 kilograms and specific heat capacity is 420 joules per kilogram per Kelvin, therefore my heat capacity will be equal to 0.5 times 420. Now half, again, the half of 420, that will give us 210. So its capacity is 210 joules per Kelvin. Or let me write it, joules per Kelvin. So this is the heat capacity of that body, 210 joules per Kelvin. All right, so I want to believe this is clear enough. If there's any area that is not clear, you can always drop a message. I was just thinking that you'll be able to comment, but for now, let's try. Let us manage. Okay, so do well to drop a message for me on WhatsApp. Let me know. Do well to drop a message for me on WhatsApp. Let me know. All right. Okay, if there's any question, you can also drop. If there's any question in the chat, if you are following me, please, drop a like. If you are following, please drop a like. If you are following, drop a like. Drop a reaction to show that yes, you are in the class. Drop a like. Drop a reaction to show that yes, you are following indeed. All right, so we'll proceed to a different question. The second question. Please, if you have your own question, you can drop it on the WhatsApp group. If you have a question, you can drop it on the WhatsApp group, please. All right, so I'm going to respond to that question, then we'll proceed to number 2. All right, let's come again with the second part of this question. Now, the first part addressed the specific heat capacity. And I mentioned earlier that the specific capacity is the amount of heat required to raise just one kilogram out of the entire mass of a body. Remember that kilogram is used to measure mass, understand? So I'm considering just 1 kilogram of the body, just 1 kilogram of the entire body. I'm talking about the specific heat capacity, that's C, right? Then when I am considering the Cp, that's the heat capacity. When I'm considering the heat capacity, I'm talking about if this amount of heat is for one, what about for everything? What about for the entire mass of that body? What about for the entire mass of that body? Okay, the heat that is required to raise the entire mass of the body is what is called heat capacity. And that heat capacity is giving us the mass, the entire mass of the body times the specific heat capacity. Okay, so to get your heat capacity, you need to multiply the entire mass by the specific heat capacity. The entire mass of this metal block is 0.5 kilograms. And the specific heat capacity that we obtained from here is 420 joules per kilogram per Kelvin. To quickly slot this into this, we have that 0.5 times 420 will give us 210 joules per Kelvin. So that's its capacity. Here is the specific heat capacity. Do not get them twisted. They are not the same thing. Specific heat capacity is talking about just 1 kilogram, or let me put this with just one molecule out of a number of molecules that make up the body. While heat capacity is considering all the molecules or all the whole mass of the body. All right. So I want to believe this is a clear enough explanation. All right. Once again, if you are joining us outside of the group, please you can drop a message to me directly in my DM on WhatsApp. If you're in Nigeria, that's 081-2121-6596. 081-2121-6596. If you are from the international sphere, you can drop or message me on +234 8121216596. 2 + 234 All right. So please confirm that you understand. Please confirm that you understand the explanation. I'm about to proceed to number 2. About to proceed to number 2. If you are there, please drop a reaction. Do not forget that one main key to excellence and success is total participation. Total participation, taking away every form of distraction, no matter the form it is coming from. It could be your phone, it could be your social media platforms. Here's the time to please stay off for just a while and you'll be back. But please, for now, I need everyone to be attentive. I need everyone to be 100% present in the class. I need everyone to be 100% present in the class. Please, if you're in the class, drop a reaction. Drop a reaction if you're in the class. Drop a reaction. All right, so we proceed to number 2. I'm going to write this on the board so that everybody will be on one page. Okay. So say number 2 here says a body of mass 2 kilograms has a specific heat capacity of 900 joules per kilogram per Kelvin. It says calculate the quantity of heat. Calculate the quantity of heat. The quantity of heat required to raise its temperature from 25 degrees Celsius to 75 degrees Celsius. All right, so here's another question that we must provide a solution to. All right, so do not forget once again that the first step we usually take is to list out all parameters given. All right, and understand the question actually. Understand the question very well. Now, the question says a body of mass 2 kg. All right, so it means that we already know the mass of the body. It's given to us that m mass is equal to 2 kg. Okay, so that's the mass of the body. It says has a specific heat capacity of 900 joules per kilogram per Kelvin. The specific heat capacity is given as 900 joules per kilogram per Kelvin. That's the specific heat capacity. Now went further to say, okay, calculate the quantity of heat required to raise its temperature. So we're looking for quantity of heat. That's looking for H. H is not known. That's what we are looking for. What quantity of heat was added to the body that caused it to move from 25 degrees Celsius to 75 degrees Celsius? It means the body will undergo a temperature change from theta 1 from 25. So theta 1 is my 25 degrees Celsius. So 75 degrees Celsius. That means my theta 2, which is my final temperature, 75 degrees Celsius. All right. What amount of heat will cause this increase in temperature? Knowing fully well that the body that is receiving the heat has a specific heat capacity of 900 joules per kilogram per Kelvin, and that mass of that body is 2 kg. Okay, so which formula will help me to obtain the heat energy or the quantity of heat that is required? That formula is simply H equals mc theta 2 minus theta 1. All right, so H, that's for heat, will be equal to, what's the mass of the body? That's 2 kilograms. 2 times, what's the specific heat capacity of this body? That's 900 times my theta 2 is 75 minus my theta 1 is 25. So total heat energy will be equals 2 times 900 will give me that's 0018, that's 1800, right? Times 75 minus 25 will give me 50, if I'm not mistaken. Yes, that will be equals to what? To 50. So what would be my final answer? 1800 times 50. That should give me 0, 0, and 0. Okay, 5 times 8 will give me 40. That's another 0, right? Then 5 times 1, that's 5. 5 plus 4, that's 9 thereabouts. Yes, so that will give me 90,000. That will give me 90,000. Yes, so this is 90,000 joules. 90,000 joules, or if I place this in kilojoules, it will be 90 kilojoules of energy. Okay, so the body will require 9,000 joules or 90 kilojoules of heat to raise its temperature from 25 to 75 degrees Celsius. So this is the solution to this particular question. I want to believe this one is also clear. Please, if there is a gray area, an area that is not clear, please also let me know. a body of mass 2 kg has a specific heat capacity of 900 joules per kilogram per Kelvin. Calculate the quantity of heat required to raise its temperature from 25 degrees Celsius to 75 degrees Celsius. Clear enough, right? Please confirm if you understand this one also before we proceed. Is this clear enough? Please, if it's clear enough, please drop a message on the group. If it's clear enough, please drop a message on the group indicating yes, it is clear. If it's clear enough, please drop a message on the group indicating it is clear. If it's clear enough, drop a message to indicate that it is clear. Are we good to go? A part that is still not clear to you, please indicate. Is there a part not clear to you? Please indicate. Okay. Okay, let me attend to this. I'm waiting. I'm waiting. All right, so let's quickly proceed. All right, so aside these other situations, okay, this light is pretty much entering my eyes, so I'm going to put it off. All right, so sorry for that. There are other situations. There are other situations that occurs where one body is losing heat and one body is gaining heat. Okay, in measuring heat energy. That's one situation that also occurs. I told us earlier that when it flows, that heat flows because there is a difference in temperature. All right. So the body that receives the heat from another body, that body gains the heat. All right. While the body that gives that heat away, that body loses what? Loses heat. For example, I carry a block. Should I say I heated a block of metal? All right. I heated a block of metal, and I placed or I dipped that block of metal into a bowl of water. Originally at, let's say the bowl of water was originally at 20 degrees Celsius, and I heated this metal to a temperature of, let's say, 1,000 degrees Celsius. All right. Now, being that the metal is at a higher temperature, when I transfer that metal into the bowl of water, one thing that will happen is that that bowl of water heats up. Okay, as it heats up, its temperature increases. So that water will move from 20 degrees Celsius to a higher temperature. Okay, it will move to a higher temperature until the final temperature is now the equilibrium temperature, where the temperature of the liquid will be the same as the metal. All right, so that metal at 1,000 joules or at 1,000 degrees Celsius will start to lose its heat. It means it will start to drop from 1,000 down to 900, down to 800, down to 600. All right, so the body losing heat, the temperature tend to reduce, while the body gaining heat, the temperature tends to increase. All right, the temperature of the body losing heat will continue to reduce, while the temperature of the body gaining heat will continue to increase until thermal equilibrium is achieved. It means that until a final temperature is obtained where both the liquid, that's the liquid water, and the metal block, they are now at the same temperature. Let's say they meet at 90 degrees Celsius. All right, so at that point, the metal block, the final temperature of the metal block will be 90 degrees Celsius, while the final temperature of the water will also be 90 degrees Celsius. All right, that is a situation of thermal equilibrium. All right, so what if you come across such a question in an examination condition where one body loses it to the other? How are you going to handle it? All right, so let's see a situation. All right, we actually have two methods of measuring heat. We actually have two methods for what? For measuring heat. One of the methods is usually the electrical method. The electrical method where an electrical energy source is converted to heat. All right, so we have the electrical method. Then two, we have the method of mixture. Method of mixture. This is the one I explained just now. All right, where I put in a bowl a metal block, like I practically mixed a hot metal block with an amount of water. Okay, that is what's called the method of what? Of mixture. Or I pour in very hot water into a cold bucket of water. Okay, after some time, since they are the same liquid, the water becomes one, being at the same temperature, because the hotter water will lose an amount of heat to the cold water until both of them will attain the same temperature values, thermal equilibrium. All right, so there is loss of heat and there is gain of heat until thermal equilibrium. That is called the method of what? Of mixture. Then electrical method is used in a situation where we have immersion heater or electrical heater, okay, where electrical heat energy is converted to mechanical heat energy. From the heater, the elements in the heater convert electrical energy to heat energy. That heat is now transferred to the bowl of water, causing the bowl of water to increase in temperature. So in that situation, in both of these situations, we have that heat loss again. Heat lost is always equal to heat what? Heat gained. For electrical method, we should not forget that electrical method involves electrical heat energy, and we know that electrical heat energy is given as IVT. IVT is electrical heat energy, or it can be I squared RT. Okay, it can be I squared RT. It can even be PT. All right, it can be PT. I think also it can be V squared R. I think so. Yeah, it should be V squared R. I'm coming on. Let me confirm this. All right. Yeah, V squared over R can be V squared over RT. Okay, so this can be the form our heat energy can take. All right. So electrical heat energy is equal to IVT or I squared RT or PT or V squared T over R, where I here stands for the electrical current. The electrical current. R here stands for the electrical resistance of the electrical material. T here stands for the time through which that current flows through the electrical heater or the electrical material. Then V is the potential difference due to the electrical resistance in that particular electrical material. So that will give us the heat energy. So anytime I'm considering electrical method, heat energy IVT is always converted to mechanical energy MC delta theta. Okay, so this always happens for electrical method. IVT is equals MC delta theta. All right. So if this is true for this, now there are some peculiar cases. There are some peculiar cases where I have a calorimeter. A calorimeter is simply a bath where you carry out these heat measurements experiment, basically. All right. So when I place water in a bath and I carry a hot metal block, an heated metal block, and I place it in the calorimeter that is containing this amount of water, most times we do not neglect the heat that is lost to the calorimeter. It means that we consider the heat that is also lost to the calorimeter, not just the heat lost to the water. So if I'm placed, if I have metal block that is dipped into a calorimeter, that's CAL, and this calorimeter is containing water, that's H2O. Now, the heat that is lost by the metal block, the heat that is lost by the metal block is not just lost, in some cases, is not just lost to the water. It is also lost to the calorimeter. All right. So in this case, we will mention that the heat lost by block is equal to the heat lost to the water. Let me call it HW plus the heat lost to the what? Calorimeter. Just like I'm in this environment now, and it happens that I'm at a higher temperature than all the materials in this particular space. I'm at a higher temperature than this particular board, and at the same time I'm at a higher temperature than my writing pen, that's my marker. All right, what will happen is that I will not just lose it to my marker. All right, I will also lose it to the marker board. Okay, I will not just lose it to my marker, but also to my what? To my marker board. That's the idea. Okay, so as far as the calorimeter is containing the water, and the heat capacity of the calorimeter is not negligible, the metal block will lose heat to both of them at the same time. So the heat lost by the metal block will be equal to the heat gained by the water and the heat gained by the calorimeter. All right, so we'll see a question under this situation now. All right, so please, once again, if what I just explained makes sense, please drop a message now. Before I continue, drop a message. If you are not clear, also drop a message indicating where you do not understand, but I believe this should be clear enough. Please drop a message. Under this iteration I just highlighted, I'm going to see a question now. Under this situation I just highlighted. Okay, are we good to go? All right, so let me write on the board. Okay, coming please. Give me some time. Coming. Give me some time. Let me just sort this out quickly. We're going to continue. Coming. Okay, sorry. All right, are we on? All right, let's continue. Let's proceed with this question that we have. All right, so we have a question here now. It says, let me write it first. So please copy, be fast about it. It says 300-gram piece, a 300-gram piece of metal, a 300-gram piece of metal at 100 degrees Celsius is dropped into 400 grams of water. It's dropped into 400 grams of water at 20 degrees Celsius. Full stop. And that goes to say that if the final temperature, let me write this for short. If the final temperature is 25 degrees Celsius, calculate the specific heat capacity. Of the metal. Calculate the specific heat capacity of the metal. It means that they gave us the specific heat capacity of the of water. Let me say SHC. That's let me say CW. That's CW of water is 4,200 joules per kilogram per Kelvin. All right, so this is the specific heat capacity of water. All right, so we are going to proceed by solving this particular question. All right, so we're going to proceed by solving this particular question. It says a 300-gram piece of metal at 100 degrees Celsius is dropped into 400 grams of water. It's into 400 grams of water at 20 degrees Celsius. If the final temperature is 25 degrees Celsius, calculate the heat capacity. Calculate the heat capacity. Okay, I think I wrote that twice. Calculate the heat capacity. Calculate the heat capacity of the metal. Mind you, they did not say the specific heat capacity, right? Okay, but we know that to get heat capacity, we need to find the specific heat capacity, all right? So let's see how we can approach this particular question. All right, very easy actually. So let's go. Now, if you observe here, they did not mention the calorimeter, so it is simply a direct loss and a direct gain. Metal loses heat, water gains heat. Metal loses heat, water gains heat. Very direct. So it means the heat. Oh, how beautiful it is. So this will mean for our solution, sorry about that, I just got a call, sorry. So if heat lost by the block is equal to heat gained by water, heat lost by block, what's the formula for heat? The heat that a body loses, that formula is what we saw earlier, MC delta theta. For metal block, it will be mass of block, specific heat capacity of block, then change in temperature. Remember, for a body losing heat, I'm going to put theta 1 first before theta 2. Then this will be equal to the heat gained by the water. What's the mass of water? Specific heat capacity of water, and then the temperature change. Mind you, the body that gains heat will have a higher temperature, so it will be theta 2 minus theta 1. Okay, the theta 2 minus what? Theta 1. Sorry, I'm squeezing this into this space. I do not want to clean the question. Okay, so what's the mass of the block from our question? It says that a 300-gram piece of metal at 100 degrees Celsius. So the mass of the block, of the metal block, is 300 grams. When we are solving, all parameters or all quantities must be represented in SI units. So this is giving us 0.3 kilograms. That's the mass of the metal block. And the initial temperature of the metal block is 100 degrees Celsius. I will call that first temperature my theta 1. Should I call it theta 1? No. Let me just say temperature of block. Okay, that'll give me 100 degrees Celsius. Okay, then after that, what other parameters did you see? We say it is dropped into metal of mixture. It is dropped into, all right? That is metal of what? Of mixture. So if it is dropped into 400 grams of water, MW is 400 grams, which is equivalent to 0.4 kilograms. Which is equivalent to what? 0.4 what? Kilograms. This water is at 20 degrees Celsius. It means that it was, let's say, initially at 20 degrees Celsius. So theta W will be 20 degrees Celsius. Then after some time, we're now giving an extra information that the final temperature of the mixture, that is the metal and the water, their final temperature was found to be 25 degrees Celsius. 25 degrees Celsius. Now they say we should find the heat capacity of the metal. And we know that heat capacity is gotten from mass times specific heat capacity. So there's a need to find CB. So when we get CB, we'll be able to find the CP of the metal. So we need to get the specific heat capacity of the metal first to help us obtain the heat capacity. So we are going to be seeing that together. Please and please, you have to stay close. You have to stay close to understand this very well. We are told to find heat capacity, not specific heat capacity. Some students usually make this particular mistake. They hurry into questions and they miss, or they tend to miss out certain details. Some persons will solve for specific heat capacity and they will leave it. But that is not the final answer. The question here says calculate the heat capacity. But I know before I can get heat capacity, I must first of all obtain the specific heat capacity. How do I solve that now? Allow me to claim this question I wrote earlier because we have all that we needed. So I'm going to rewrite this my formula. Mass of block, allow me to rewrite it. That's the metal. Specific heat capacity of metal. Then my theta 1 will be the initial temperature. That's the theta B. That's the initial temperature of the block minus the final temperature of the whole mixture, theta F. This will be equal to the mass of water times the specific heat capacity of water, which is into the bracket. Now, for water, the final temperature is greater than the initial temperature of water. That's 20. So that's theta W. Alright? So this is same thing as this. Theta B is the initial temperature of the metal. Theta F is the final temperature of both the metal and the water. while theta W is the temperature of just the water initially. So I'm going to plug in my values. Okay, mind you, I'm looking for CB. So my mass is 0.3 times unknown CB times into bracket theta B is 100 minus theta F is 25. This will be equal to the mass of water. The mass of water is given as 0.4. Specific heat capacity of water from the question was given to us as 4,200 times, then into the bracket what is F, the final temperature of both the metal and the water, that's 25, while the initial temperature of water, that's 20. Okay, so 100 minus 25 will give me 75, if I'm not mistaken. That will give me 75. So if you're with your calculators, let's punch together. Let's punch our calculators together. 100 minus 25 will give me 75. Yes, will give me 75. So 0.3 times 0.3 times 75. That'll give me 22. So 22.5 CB will be equal to 25 minus 20 will give me 5. So 5 times 0.4, that should give me 2 if I'm not mistaken. 0.4 times 5. Yes. 0.4 times 5, that's 2. 2 times 4,200, that will give me 8,400. 0.4 times 5 is 2. 2 times 4,200 will give me 8,400. So my CB, which is the specific heat capacity of the metal, will be 8,400 divided by 22.5. So specific heat capacity CB 8,400. If you are there, please participate along. 8,400 divided by 22.5. That will be 373.33 joules per kilogram per Kelvin. So this is the specific heat capacity of the metal, not the final answer, because the question says calculate the heat capacity. So if this is the specific heat capacity, therefore Cp, which is my heat capacity, like we saw from the previous question, that Cp is equal to the total mass of the body times the specific heat capacity. In this case, it is for metal. So what's the mass of the metal? 0.3. So this will be 0.3 times 373.33. Therefore, my heat capacity will be 0.3 times 373.33. This will give me 111 point okay, that's approximately, let me just say approximately 112 joules per Kelvin. So that's the final answer to this beautiful question. 112 joules per Kelvin for the heat capacity of the metal. I want to believe this question is also very clear. If there are any gray areas, like I'm very open for it. If there are any gray areas, please do well to draw my attention to it on WhatsApp. If there are any gray areas, draw my attention to it on WhatsApp. This is the heat capacity, the solution to the question I dropped earlier. Any further questions, or if there's a question that you have from your textbook or from your personal study, you can drop it. Together, we are going to solve it. I'm waiting for it in my DM. Can you hear me, please? Confirm. If you're on the call, can you hear me? Confirm, please. If you're on the call, can you hear me? Confirm, please. If you're on the call, confirm. Can you hear me? If you're on the call, confirm. Can you hear me? Can I be heard? If you're on the call, please confirm that. Confirm that you can hear me loud and clear. All right. So, does anyone have issues with the solution on the board? Does anyone have any issue with the solution on the board? If there's a problem somewhere, something is not clear, you need me to explain further, please let me know. Does anyone have issues with the solution on the board? Does anyone have issues with the solution on the board? If there's a problem somewhere, something is not clear, you need me to explain further. Let me know, please. If it's not clear, please let me know. Can you hear me? Are we all carried? Are we all carried? David, are you there? Ali Amin, are you on the call? Miss Soma, are you on the call? Umi, are you on the call? All right, so we have pretty much done justice to this first level of measurement, where we have seen the situation where a body receives heat and it causes a change in its temperature. From that, we can measure the specific heat capacity of that body. All right? We have seen the situation where a particular body loses heat to another body, like this question that is on the board, where a metal at a higher temperature loses heat to water at a lower temperature, right? So this is the first level for measurement of heat under heat capacity. Now there are other situations which we are going to discuss by next week Sunday, but I want them to do something. All right, next week Sunday before we will start, I would entertain questions. It means that between today and next week Sunday, I want you to send all questions bordering on heat measurements and heat capacity. So when we come next week Sunday, what we will do at first is to provide solutions to those questions, in details before we proceed to seeing other questions that has to do with it being lost to both a material and the container of that material. After that, we also consider a bit of electrical method. They are similar, all right? We also consider a bit of electrical method before we delve into change of states. Where we'll be considering latent heat. We also consider latent heat of fusion, latent heat of vaporization, as well as specific latent heat of fusion and specific latent heat of vaporization. Heat measurement is one beautiful, amazing part of physics that if only you pay attention to, like you pay attention to how much details I've just given concerning this particular topic, you should have no problem with this particular topic. All right. So I'm going to give a 5 minutes countdown. Please, if there are any questions, drop it in my DM. I'm going to answer them before the end of this live class. All right. So please check your textbook, check those notes that you have written on before, questions that you have highlighted under this, that you have always looked for answers to. You can drop it now in the DM. Let's see if you can answer them before it is time. All right, so I'm going to be waiting. I'm going to be giving us 2 minutes. 2 minutes. I'm going to give us 2 minutes. Please drop it in the DM. Whilst you are doing that, let me just say this. This is Polamine. Polamine, and I welcome you to Physics with Polamine. All right, Physics with Polamine. What do? We render seamless physics classes that makes physics easier to comprehend. We usually say that, yeah, physics is made easy. Physics is made easy, and physics is all about mathematics also. So you are looking forward to also dropping some mathematical solutions to some mathematical problems as the time goes on. The end goal is that whatever exam that you will be sitting, if you stay committed to this channel, if you stay committed to the classes that we usually have here, we'll be having live classes like this one, and we'll be having short videos to solutions, short videos of certain concept, explanation to certain concepts. We'll be sharing it on this particular channel. I urge you to try to always make yourself available. Trust me, if you stay true to these classes that we are having and you pay attention to it without any form of distractions, I can assure you that whatever exam you are writing, be it physics, WAEC exams, be it in your UTME, post UTME, even if you do are just here to just gather knowledge on one or two physics concepts, I can assure you that your journey, or rather the outcome, will be a very, very, very plausible one. All right. So thank you once again for being a part of our today's class, or being a part of our today's class. This would not be possible if you are not here. Okay. So it was because of you that I am here today. It was because of you that this class came up live here on YouTube. All right. So if you are yet to subscribe to my YouTube channel, please drop a subscription. Just press subscribe. Just go. No, it's not difficult. The button is not too hard. I think that's the softest button ever. Just touch subscribe button. All right. You can also drop likes, and hopefully soon the comment section will be open. You can also drop comments and share this channel, and also share this live video to as many persons who need this, or who would need this to help them ace their exams. Thank you very much, and God bless you. I'm going to wait for like 1 minute more before this live goes off. All right, so we'll call it off for today. It has been an amazing 2 hours of talking about physics. Okay, please, and please, next another time that I'll be meeting. If you come across this video anytime from now, if you are seeing this video as at this time when the live has ended, please do not forget, here is where physics is made easy. Okay, so if you want value like this in physics and mathematics, please do well to subscribe to this channel and expect more classes as this. Next week Sunday we'll meet again to talk about part 2 on its measurement and its capacity. Thank you very much for being a part of this section. God bless you.